Okay, great. I think the streaming on YouTube has also started. So a very warm welcome everyone to our usual weekly live stream. To both those of you who have joined us on Zoom, thanks very much. And those who are watching live on YouTube. As always, if you're watching on YouTube, please feel free to post your questions in the chat as we go along. And if you have joined us on Zoom, then you can post your questions either in the Zoom chat or feel free to unmute yourselves and just join the discussion at any point. So for today's live stream, we will be solving, I think, a couple of problems that were released together, although they come from two separate weeks. This is perhaps because the week 5 programming assignment was slightly delayed and it was released along with week 6 with a common deadline. So the week 5 and the week 6 programming assignments will get discussed today. And just in case we have some time left, we will probably do a bonus problem. But the main agenda is to do the 5 and 6 programming assignments. And as I shared on Discord, today's session will be managed by Nipun and Yash. I'm not sure who is going first, but please feel free to go ahead, either of you. Thanks so much.
So thank you, ma'am. So I'll be going first with week 5 programming assignment. So just a minute, I'll share my screen. So I hope my screen is visible. Can someone confirm?
Yes, sir.
Yeah.
So in week 5, we had this question, Tom, Jerry, and a maze. So in this question, we have a maze which is a grid of h cross with the dimension h cross w, h times w with h rows and w columns. So in each cell, so in this grid, each cell either is denoted by an hashtag symbol or a dot symbol. So what dot indicates that the grid is that grid is a free, that square is a free square, and if there is a hashtag symbol, a hash symbol, it implies that there is an obstacle. So what do we have to do in this question? So in this question, Tom will choose a particular cell as an origin and another square as a target. So what Jerry has to do, he has to travel from the origin to the target. But now what Tom wants is that distance, like the distance between the origin and target, should be as much as possible. And Jerry is only allowed to travel vertically and horizontally, but he cannot travel into a obstacle square. So this is the question, and we have to maximum possible number of moves Jerry has to make so that Tom can choose any origin and target square. So basically we have to find a maximum number of moves possible. So I hope the question is clear to all of you. Does anyone want to share their approaches? Anyone?
Sir, could you please repeat once again if possible?
Yes, someone speaking. Can you speak again?
Yeah, I'm not sure if somebody was asking for a clarification or if they had an approach. If it was either of those, feel free to just unmute yourselves again.
So I don't. Okay, someone
Yeah.
do a BFS. Basically we definitely have to do BFS, but there are some things to it. So before like looking at this question, one might not think how to apply, how to use a BFS or something like that. So let's look at the question. Let's look at a simple example. So this is a 3x3 grid. You can see straight away that I can ask Tom to set this as the origin and set this as the target, and this will be the maximum distance which Jerry have to cover. Like he can go like this and travel a distance of 4 squares. So for this example, but you can certainly put so what if I sorry, what if I do something like this? Suppose cross is the obstacles. Now Jerry has to travel along this path. So the distance will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The distance will be 10. So now the question is, how will we use BFS to get our solve this question? So definitely, if you want to use BFS, okay. Yeah. So if you want to use BFS, you might want to construct a graph out of this like this arrangement which we are given. So what we can do? So every square will be a vertex in the graph, and every square will be a vertex in the graph, and its adjacent will be its neighbors. So all its adjacent vertically and horizontally adjacent squares will be its neighbors. So we can construct a graph out of this. We can construct a graph using that, and what we can do is so we take every possible vertex which is free and run a BFS on a graph on the graph, and we will exclude these obstacles which are not free in the BFS. So what we can do, we'll run BFS on we'll run BFS on this vertex which we have selected, and we'll get at least one vertex which will be furthest from this furthest from the selected node. So we will save that as the maximum, some kind of maximum. So maximum distance, something like that. And then we select the next node. We select the next square of vertex which is free, and we run BFS again, and we keep updating the max distance in from this iteration. And finally, after all the we have run BFS on every free square, after running BFS on every free square, whatever max distance we get will be the answer. So I think the idea is pretty much clear. Does anyone have any doubt in what I said? So I guess this problem is pretty much clear to everyone. This wasn't even a very tough question. So maybe if no one has any doubt, maybe we can move further and let Nipun continue.
Sure, that sounds good. I think if you're going to be around, yes, if there are questions in the chat, then you can address them. But Nipun, you're welcome to take over, talk about the next problem.
Sure, ma'am. Just to make sure, am I audible?
Yes, yes.
Perfect. Okay. I'll just share my screen. Hope my screen is visible.
Yeah.
Yes, sir.
Okay, cool. So basically, the problem is that you have a person who, and there are end states. There is a network of end state which are connected by bidirectional roads, and the number of edges. If you are modeling this as a graph problem, so there are end state that is n vertices, and there are bidirectional roads that are edges. And it's you can. Okay, let's talk about logistics later, maybe. And for each road, you need a certain amount of fuel that you need to transfer through it, and once you have and basically you are given a source vertex and a target vertex, and you want to say that how much cost is it going to bear you for transversing through the network, right? So these are the two states P and Q, and these are the starting and the final state you want to transverse, and how you're going to transverse through the network will determine how much cost you're going to pay. This is a fairly, I think, lengthy question just to understand. So I just want to make sure everyone understands the question. So does anyone want me to repeat the problem statement, or everyone is clear with the logistics of the question?
Simply repeat.
Okay, sure. So basically you have n states, and there are bidirectional roads. The total number of roads that are connecting the every state with the other states is R. And for each road, you need some fuel to transverse through it. Okay. And once you reach a particular state and you're exploring within the cities, there is no additional cost. So for example, if you start with from this state and you go to this state, so from start with I and J, and you park your car in J, then basically there is no additional cost. And for example, the you're going from state I to state J, and the cost associated is F. So basically, if this was your start state and this was your target state, then you can say that cost of transversing from S to T was F. Okay. Uh, yeah. And if you go from J to I, then the cost will remain as F because these are bidirectional roads, right? And for each I, basically, and for each state, there is a price of the fuel. So basically, at each state, you have to at some states, you may need to refuel your car, and there is a cost associated with that refueling. And we can say that it is RW. So if you refuel your car with X units of fuel at state I, then your cost will be W into X. Is this clear?
Yes, sir. I got it. Thank you, sir.
Okay. Okay, that is perfect. Sure. Yeah, and then there is some logistics on the input, how the input has been laid out for coding examples. We'll go look into that later. And first is the basic intuition. So, okay. So just by looking at this problem, it's a classic example of a network problem. And you can say that there are n states and there are I bidirectional roads. And if you visualize that, it is more or like a graph. So I can say that I have n vertices in laid here, and there are the n vertices, and there are some R roads. And you can say that each road is basically, so if I say that there is a road between these two states, so this is basically a bidirectional road. So I can go from this state to this state, or from 1 to 2, or from 2 to 1 with the same cost, because these are bidirectional roads. I Okay, so that is enough motivation for the problem. Okay, and so basically the question is, you there might be a situation that this is your starting state and this is your targeting state. The state you this is in the notation of the problem, this is P and this is Q, and there might be many ways in which you can reach P to Q. So the first question that arises is, what path should we follow? Like, there are many paths possible. This might be this path, first path, second path, third path. Which path should we follow? Right. So we'll just go
I
step
think
by step.
shortest.
Sorry.
No, I think shortest path we have to check.
Okay, shortest path. I think, yeah, that's a good assumption to begin with, or yeah, that's a good motivation. So we can say that take the shortest path trivially, and once we have the path, the shortest path length, we can do something on the path, because in the question you are asked to return the cost of your transversing. So you're going from P to Q, and you don't have to output the path. You have to say what is the minimum cost. So let's say you got the shortest path from P to Q. So let's say this was a very complex graph. Okay. And you somehow managed to get the shortest path from S to T using maybe using Floyd-Warshall algorithm, or Dijkstra's algorithm, trivially Dijkstra algorithm, since weights are non-negative. And to model this problem as a graph, if I have not been clear enough, so there are n vertices, which are the states. There are 2 into r edges, because you can say that it is a directed graph. And then there is, each edge has an weight w, and the weight is basically the cost of traversing through the edge. Please feel free to stop me at any time if it gets too cumbersome or anything like that. And let's say you managed to get this as the shortest path among all the paths in the graph. And so x, y, z uh, are basically the amount you need to pay for refueling your car at state 1, 2, 3. So this is state 1, 2, and 3, and XYZ are the cost you need to pay for refilling the car. Right. So basically, so if X is less than Y is less than Z, so I can say that I will refuel my car at this state for the whole journey. And I can basically say, because if I refuel it like 20x plus 30y plus 40z, basically refueling the car at this stop for this interval, refueling the car at this stop for this interval, and this stop for this interval, then basically this is larger than this cost, right? So this is larger. So my optimal answer would be just I stop at X and refuel it for the whole journey, and then just drive all the way to T along my shortest path. Is this clear? Is this clear? Why is this the optimal I can do if I have the shortest path?
So actually, I'm not able to hear last point. Could you please last point?
The last point, as in, why is this the cost? Do you want me to repeat as to why is this the cost?
No, I got it now. No, I got it.
Okay, perfect. Right. And basically, so this is another case. If I say that I can maybe put some values here. So if I say X is, maybe for this case, I'm talking about this case, just to be clear. For this case, I can say X is 10, Y is 20, and Z is 5, right? So my cost would be, first I refuel at X, and then I drive all the way from X to Y, right? Because Y has the higher cost, so I won't want to refuel at Y. And then once I reach at Z, since it has a lower cost than X, then I'll refuel from Z to target. So this will be the optimal in this case, right? But the thing is, when you find the shortest path and you do all this, this is still not the optimal for what the question has asked you. So just, can anyone tell me why this strategy doesn't work? Like, if you just find the shortest path trivially and then do all this, run this algorithm, this still fails. It is not the,
Because of fuel costs.
sorry, I think someone was saying something.
Because of fuel tank capacity,
Because of the,
tanks capacity.
because of the capacity.
No, capacity is unlimited, right? We can store as much fuel as we want.
Right, capacity is unlimited. You can store as much fuel. There's no bottleneck on how much fuel you can carry for any number of iterations.
I think,
So which one were you saying that was not optimal?
Okay, I meant, for example, if you have, I'll just repeat this. So you want me to go over this part? Why this is not the optimal?
Yeah, because this is the shortest path and we're refueling at X, which has the minimum cost of fuel.
Right. I'm saying this is the optimal case if I have the shortest path. But I'm saying that if I give you, is there an instance of a graph situation which I give you and you find the shortest path from S to T, but it's still not the right answer for the problem?
Yeah,
I'm
if we
saying,
take a longer route and if the fuel cost is considerably lower, so that the overall cost is lower, then it will not be optimal.
right, exactly. I think that was just what I was going for. Thank you for answering that. And basically, okay, so this statement which I've just written is basically what you do once you find the shortest path. But the shortest path would work. But this fails. For example, let's take this situation. So you have the S2 vertices which are highlighted with green and light blue respectively, and the edge weights in red are basically the cost situated with each edge on transversing that directional road. Notice that I have laid this as a undirected network here because in the question the roads are bidirectional. So basically transversing to and fro has the same cost. So I just flattened my network as just to be clear, this is undirected, right? And this still fails in this scenario. I'll just tell you why. So here, if I run Dijkstra algorithm, I'll just consider the edge weights and basically what. So let's first of all let's say what will be the optimal answer. So can anyone tell me what should be the optimal cost of traversing from
600.
600?
600.
Okay,
Yeah.
how?
Like from 10 to 2, the nodes are labeled 10 and 2. So that cost is 500, and from 2 to 11, that is 2 into 50, that's 100. So 600.
600, right? Okay, so you are following. If I'm not wrong, you are following this path, and you say that your optimal path is this, right?
Yeah, so we're starting from the first starting node and then we're refueling at the second node.
Perfect. Right. Okay. So you have only that much fuel. You need from 10 to 2. And after you exhausted your fuel, you are refueling again at 2 and then going all the way to 11. Node labeled 11. Okay, perfect. But if I run Dijkstra here, so just to get the shortest path, if I run Dijkstra here, so from 10 to 11, this is my shortest path. I'm sorry. This is my shortest path because here the edge weights add up to 90 and here the edge weights add up to 100. Right? So Dijkstra will return this as the shortest path. So notice my algorithm was basically take the shortest path, return the path, and do something on the path, right? And once I have the shortest path, this is my shortest path, and even if I try to get the lowest cost on my path, then that would be basically
690.
690.
690. Yeah.
Right. Basically, you 10 into 20, then you
Yeah, 10
exhaust
into
the fuel.
20 and then we refuel at
7
7.
into
This
7 into
70.
4 into 90. 4 into 9.
No, this
No,
won't
no, no.
be.
You don't refuel at 9. You refuel at 7 and then for the
Yeah,
Acha, acha, acha. Yeah.
yeah, 70
because
into 7, 490 and plus 200, 690.
yeah, perfect. 690. Okay. Right. So basically this is So the problem is basically in choosing the path, and once you can choose the path, then basically you can do something along the path. Okay, and then there's the next intuition is basically for because once we were choosing the path, we were not taking account of the associated weights. Sorry, I mean the cost of refueling at each vertex. We were only talking. We were only taking account that how much fuel you need to transverse NH, right? So what happens if you multiply edge weights with the cost of transaction, and by transaction I mean transversing along an edge. Okay, so I just update each edge weight as the cost associated with either of the vertices, and if so in my convention, this is a pretty basic convention. If I am transversing, because for transversing I will probably do a BFS or DFS. So if I transverse along this edge, so I'll take my first vertex, multiply with this edge, take my second vertex, multiply with this edge, take my third vertex, multiply with this edge. Okay, and for this network, I'm using the same network. Yeah, so this will be 10 into 20, 7 into 30, 9 into 40. Is this clear for how this problem? So this is my updated edge weight for the same network, for the same graph. Okay.
Okay, we're not taking the minimum cost rate directly.
Yeah, I'm saying because you're anyway going to transverse from this to this, you're going from this to this path, like starting from 10 to 11. So I'll just take the first vertex I encounter. Okay.
Why are we doing this again?
This is just for intuition. Maybe, okay, your point is right. Maybe I'll need to do some logistics to get hold of probably. Okay, so basically you want to update the edge weights in a sense that will give you the path you need to follow to reach from S to T. And maybe you want to build an intuition along something like, so if I have this path, then if I'm going along this path, then I'll update it 10 and 7. I have no choice. I will have to update this with 10 into something. And if this cost is probably higher than 10, then I update it all the way along here. And if this falls from 10, I update with a different value. This is your intuition, right?
So we are doing a DFS.
Yeah, you can say that we are going to DFS, and once we are transversing through the edges, we are just updating the weights with edge weights with the refueling into the next edge you want to transverse.
Okay, sir.
Right. Basically, I want to update my network in the sense that I want to once I can have an idea of what is the minimum cost along all possible paths. So basically, this updating, even if you want to account for the cost, this still fails. And this is because, so for this network, which I've drawn, if I update along this path and this path, then this will be 200 plus 600. Wait, I think I just got some edge weights wrong. Yeah, so basically, if I'm updating along this path, then this graph reduces to this graph 200, 600, 800, 500, and 940. And if I want the optimal answer in this problem, then this is again 900. For this graph, the optimal answer is 900. Can everyone see that? Why this is 900?
Yeah.
Okay. But and for 900, I'm following this path, right? And here, so if I run a probably Dijkstra from S to T, here I'll get a cost from 1640, and here I get a cost from 1450, right? So Dijkstra will say that, okay, you need to transverse to this path to get the minimum possible cost, and then you need to run some other algorithm to probably understand what your minimum cost is. I am building this intuition as to know that which path. Firstly, I should know which path I'm going to take, and then I will transpose to the path, and then I will do some heuristics to just know what is the minimum cost. Okay, so this still fails. Right. So this is the test case from the problem. Um, if you just log into your page and you just see the first test case, this is the first test case. I've just abstracted it out in a graphical network. And remember, the roads are bidirectional, so you can go from 2 to 4, and then you can go from 4 to 2 with the same cost. And by cost, I mean the fuel you need to exhaust, right? So what is the idea for the optimal algorithm? So just before discussing further, does anyone have any other intuition we can build to know what's the best we can do for this situation?
I think we already discussed that the DFS, but with not just multiplying the node with the edge, the next edge length, we multiply the minimum encountered.
Right. So you are saying just the minimum encountered. So for this graph,
Yeah.
if I have, let's just keep it 20, 30, 40, 50, 50. And if this is 10, this is 12, and this is 7, this is probably 8,
Yeah.
right?
So if we traverse from, we do DFS, right? So we go
Okay.
from, like initially the intuition would be to go to the minimum side. So we check the edge, weights, the node weights of both sides, and the minimum weight is at 8. So we first go to 8 from 10. So 10 into 50 is 500, and then 8 into 50 is like 400, right? So 500 into plus 400, 900.
Just can you just tell me once which two weights are you checking for minimum, 10 or 8 or 10 or 12 or 12 or 8?
12 and 8. For
Okay,
the
so you're
DFS, for the DFS, that's what I'm checking.
right. So basically not accounting for the edge length, right? I mean the edge weight.
Yes. Yes. Okay, I should. Wait.
Yeah,
I'm
you
sorry.
should.
I'm sorry. Yeah.
Yeah, so I think that's a very nice intuition, by the way. And I think basically like, on every step you're greedily taking the. So if you at any step, so if I'll just generalize your intuition at any step. So if you're a vertex I and you have two vertices, you have um, n possible path from I, and then you basically take the minimum weights of all the vertices, and you just um, I mean take the minimum what take the minimum weight from all of these vertices, and whatever is the minimum, you go along this path, and then you keep on doing the same. So that's the intuition. But the problem is you're not accounting for the edge lengths or how much you need to pay, right? Um, so
Right.
so right. Okay, so if you think about this whole problem, um,
But the main point was that
as
instead of multiplying the node to the next edge length, we multiply the least encountered node weight. So we go from
yeah,
10, 12 to 7. We first multiply 10 into 20, and then because 10 is the minimum encountered weight till now. 10 is the minimum encountered fuel cost. We multiply 10 into 30 to get that edge length, and so on.
right, and then for you do this for every path, right?
Yeah, for every path.
Right. So basically, you're trying to build another graph out of this, and so now you have encountered 10 into 20, and then you say, if I'm following this path and this has a cost of refueling 12, but I already can refuel it with 10, so I'll refuel it with 10. So if I encounter a lower cost 7, I'll stop refueling till here, and then I refuel all the way from 7. This is what you're saying.
Yes, sir. But I don't know how
Yeah.
computationally intense this would be compared to brute force. So
Yeah.
you're just finding paths. So you're finding all the paths, and then you're doing this. So
Right. Basically, you're trying every possible path you can get, because in DFS you will have every possible, you will be traversing through every possible path from S to T, and that would be basically the order of um, uh, E, I think, order of E into
Yeah,
log
order
n
of A.
probably.
Yeah. Hmm.
Yeah. Uh,
Sorry,
so I
what
think,
would be its order?
I mean, if you are just talking about a simple DFS, then the complexity of DFS would be you're basically processing through every possible edge, right? So that would be and that would, I think, order of
V plus E,
yeah, V plus E, and then would be order of E.
order of E. Yeah.
Yeah, so DFS would be order of V plus E, and then in turn that is order of E, or order of V square for upper bound.
I think it was V plus E log of E or something.
That depends if you are using I think priority key or something like that, but in general your V plus C, because you encounter every vertex, then you encounter every possible edge, because you're transversing. BFS means you're transversing the whole edge, and intuitionally speaking, you need to encounter every edge to know every possible paths, right? So that would be order of E, and then you visit the vertices also, then that's order of V. So order of V plus E.
Okay.
And I say because in most cases I can for in this situation, as the number of edges is basically order of n square probably. So I say that order of n plus n square is order of n square. I this intuition is pretty much right, but in the sense that if you're trying um, every possible case, this is pretty much not. I won't say this is brute force, but you're trying every possible path, right? So I think we
Yeah.
can do better than this. So the idea is that, okay, if I'm going from S to T, there are many possible ways I can take, and there are many possible paths I can take. So what I'll say is, okay, let if I go for from a vertex uh, U to V directly without any this is not a direct edge. There is a path. Without refueling, I only refuel at U. What is the cost of my whole journey? Did you get the intuition? So
Okay.
I go from for each vertex in my graph U and V, for every vertex in my graph from U and V, I go from U and V, but I don't stop anywhere. I just refuel at U. So what is the cost associated with this? And I can say that if I know this for every vertex U and V, um,
We can take a path from the minimum to the next minimum and stuff, like from the back. From D to
can,
S, we can go back, and from the
uh,
minimums.
can you
Fuel cost from U to X, let's say middle point, and then from X to let's say V.
If you go to from back, you can get minimum. Yeah.
yeah. So
And
Let's
basically,
finally,
assume
at the
X is a minimum fuel
okay,
cost.
yeah, go ahead. Okay, so you're basically contradicting that. Why I think you are basically asking why, posing a situation why this might not work. So I'm not saying that I will go from S to T directly. I'm saying that I will build a new graph, okay, and this will be a complete graph. And by complete graph means if I have n vertices, then my new graph will have n square, sorry, n into n minus 1 by 2 vertices. This will be a complete graph. No edge will be missing. I can go from any vertex to any vertex. And what I'm saying that in my new graph, I will know that if I go from U to V without refueling at any X that falls in between U and V, I only refuel at U. What is the cost associated? So in this example where I had this network, so 10, 20, 30, 40, I'll say, and this is another. So 50, 50. This is not 40, right? And this is X. The cost is X of refueling at V, right? So I have two possible paths. I have this path and I have this path. I'll say that what from U to V, what is the cost of refueling from transversing from U to V without refueling at any station in between, and what is the minimum of that cost? So if I start at, this is U, this is V. If I start at U, cost of refueling along this path is basically 10 into 50 plus 50, and cost of refueling along here is 10 into x into 10 plus 20 plus 30. And whatever is the minimum of these two, I'll take that cost. Is this clear?
Yeah, it is clear. You can go on.
Yeah, so
that's it.
basically build new graph for every U comma V in the graph, such that path U to V denotes minimum of all costs of going from U to V by just refueling at U. And you don't stop in between. The condition is you don't stop in between. And I know I'll have many number of ways to go from U to V. I won't stop in between. And in this case, I have two ways, right? So I just return the minimum of these two. But now my next question is, how do you know which of these is the minimum? Like, which of this is the minimum cost? Is my question clear? I have two paths. I know that I'm only going to refuel at U. I'm not going to refuel anywhere in between. Then how do I find the shortest path from U to V?
Shortest path would be the minimum cost one, but are you asking for something else?
Yeah,
You're doing a normal diagram. So
yeah. You can run a normal Dijkstra. So basically, I know I'm only going to refuel at U. So my cost of refueling remains constant for any path I encounter. That is X. And then my cost is basically only going to change due to these edge weights, right? This will only change due to these edge weights. So here the cost is X into edge weights, X into edge weights. So I just have to minimize these edge weights I encounter, and that would be a simple Dijkstra, right? So just let's go back. So basically, what is the cost of going from U to V without stopping, and you need the minimum cost.
Can you
Okay.
give an example, please? Because I'm not clear yet. What exactly you do?
Okay, so I'm saying that if I'm going from S to T, and there are many paths I can take from S to T, right? And I'm trying to build a new graph. So in my old graph, I only have these edges, right? But in my new graph, I'll have all the possible edges, right? So this is G that is given to me, and this is G dash. Okay, these are still the same vertices. In my old graph, this edge represented what is the cost from going from vertex I to J. And in my new graph, this edge will represent what is the cost, minimum of all cost from going from vertex 1 to 2 without refueling in between. So I only refuel at vertex 1. And what is the cost from going from 1 to 2?
Understood.
This is understood, right? So I'll say that if I have a network like this, and I want the minimum cost of going from 1 to 2, right? So this is X and this is Y, and the refueling cost is probably f, and this is z, right? So I want to go from 1 to 2. Now I have two paths. I can probably take this path, or I can probably take this path. If I take this path, then my cost will be f into x. And if I take this path, my cost will be f into y plus z. I want minimum of these two. So f is constant. So I say I'll run for every u and v, I'll just run Dijkstra, and the cost will be f into shortest path, u and v, in my new graph.
Got it.
So if I say x plus, if I say y plus z is less than x, so in my new graph, the edge between 1 and 2 will be f into y plus z. I hope this is clear.
But it should be the directed graph, right? Because if we go from 2 to 1, then the cost would be
Right. Exactly. That's what I was going. That's what exactly I was going for. So this will be a directed graph, and I think you just mentioned the reason very carefully, that this will be a directed graph because here in original graph I could go from 1 to 2 and 2 to 1 easily, and this had the same cost. But in this graph, I'm saying that what is the cost of going from u to v, minimum of cost. So this is basically putting the whole problem in a directed graph. So if this is f into y plus z, and in this case, this probably will be the same cost because I don't have any other paths.
No,
Oh,
the
okay.
path would be
This
the
will be,
same. The
yeah,
path
this
would be
will
the
be, if
same. The
this is
constant
f
f
dash,
would be changed.
yeah,
Yes.
this will be f dash into y plus z. Right, so this is a directed graph. So, right. So basically we are trying to build, so I'll just write here, for every u and v in G, find the shortest path from u to v, and in G, update with into shortest path, and edge of v to u is equal to cost of v into shortest path. So this is the ng dash. This is the directed graph, and this will be complete. By complete graph, I mean it will have, between every two vertices, it will have an edge. Is this clear?
Yes, sir.
Okay, perfect. I'll just copy this so we can run this algorithm here. Okay, so let's try to with this. So this is one of the test cases, and the answer is given as 28 for the optimal cost. And 3622 that are in blue, they represent the fueling at every vertex, and 317 which are in red are the cost you need to pay for transversing an edge. Right. So let's build a network out of this. So this is G dash. So I'll let you build the network. Uh, can you tell me what will be the weight of this edge going from 1 to 2? Anyone? Weight of the edge going from 1 to 2?
1 to 2 is 9, right?
9, 3 into 3.
Right.
And
And from 2 to
2 to
1?
1 is 18.
18.
Perfect. From 2 to 3?
6.
6.
6,
Okay. 3 to 2?
2.
2,
Okay. 4 to 2?
4 to 2, 12, 14.
14,
And Uh, 42.
42.
16 said 42.
Okay. Yeah, that is I think right. So from the 4 to 2 is basically 2 into 7, 14, and 2 to 4 is 42. Then you go from 4 to 3, and so can anyone fill for 4 to 3?
16.
Right, 6 into 2. 16 from 4 to 2.
7 plus
7
1.
plus 1, 8, right,
Yeah,
16.
yeah.
And from 2 to 4?
Sorry, 3 to 4, right? 3 to 4
3 to
is
4,
again 16.
16, right. And then we go from 1 to 4.
30.
30.
And that is 20.
Yeah, that is 30, and that is 20. And 1 to 3?
4 threes are 12 and 8 the other way.
20.
Right. So basically, you go from 1 to 3. So that is 4, and that should be I think 12. And
Yeah,
from 3 to 1, that should be 8.
yeah.
Right. So I think we can work on. Okay. So can anyone give me a reason why did I create a new graph G dash? So what is the benefit that this graph will give me over my other what I mean? What is the advantage of building a new graph?
Yeah,
To
now you do a
optimize.
shortest path from here, you'll get the answer.
Yeah, but why?
By just
We are,
computing a minimum cost spanning tree.
basically, we are getting optimal solution from that.
I just wanted to ask that why will running the shortest path algorithm from S to T. So my S is 1, the vertex labeled 1, and my T is 4, vertex labeled 4. So why running the shortest path from S to T will give me
Yeah,
the optimal
because if
answer?
we go directly from 1 to 4, we know that this is the answer without refueling. But if we refuel somewhere else, we know that our cost would be lower. So we can
Right,
go from
exactly.
1 to 2 and then 4. That would give us more. So no, that won't be the optimal answer. But
No,
see,
no, right. Notice that this graph actually encaptures all the information or all the possible paths you could have encountered. So for going from U to V, so if I say I was initially going from U to V, there are only two ways. Either I can just refuel at U and transverse along the shortest path, or I along any other path, I refuel in between some vertices I, J, and K. I or I plus J. So I refuel in between J vertices along some path. Now this graph gives you the information what is the fuel if you go from I from 1 to 4 directly with just refueling once, or you go from 1 to 2, then go from 2 to 3. So this basically has all the information of all the possible permutations. You stop at 2 or probably stop at 3, then you stop at probably 1 again, and then go to 4. So all the possible of ways of reaching from 1 to 4 and all the possible permutations of fueling at any vertex can be captured using this graph. So is this statement clear? Why this
yeah,
graph is so powerful?
yes,
Right. So basically you capture all the information that as to um, where you could have stopped, where you could have fueled again, and where you could have taken the one edge over the other. And this is the whole intuition of building a new graph. And the next step is just run Dijkstra, because the weights are positive. You just run Dijkstra over this graph, and then you can get the sort of you can get your answer. So if I run Dijkstra, so I am going from 1 to 4. One path is 1 to 4, but this is this is not the optimal path. So I go from here 1 to 9. Then I'll go. I think I can just go over one from here 1 to 3, and then go from 3 to 4. So my total weight would be 12 plus 16, 28. and that is the optimal answer as given in the test case.
So you first run a Floyd-Boschel algorithm for the all shortest path, and then you use the extra here.
Yeah, I run a Floyd-Boschel algorithm for all pair shortest path. Basically, I want shortest path between every pair of vertices because I want to build a complete graph which has n into n minus 1 by 2 edges, or basically n into n minus 1 edges because every vertex has 2 edges. Right. So I use Floyd-Boschel to build G dash, and then in G dash I can run Dijkstra for having the shortest path from S to T. So this is my whole algorithm basically, and it's up to you how you can implement this in Python or C++ or in Java.
This is brilliant. Like, who came up with it, and how do we come up with something like this?
So this is basically, this algorithm is motivated by the how what basically you can do with directed graphs. And even though graph initially we were dealing with undirected graph, and the information that you lose in that undirected graph is the path information that I can go from U to V, and you're assuming that V to U is the same path, but it is not. And in the question, it is mentioned very beautifully that once you go from U to V, you incur the same cost from going from V to U. But if you just build G dash like I just built here, then you can do something better. So I hope this motivates you enough to complete the implementation part in C++ and Python. Anyone has any questions? I will be happy to answer.
How much time did it take for coming up with this?
I think I had some discussion with my colleagues also, and I think this took. I have seen a similar problem in one of the coding contests also. So this took a bit of work, but this was fine.
Okay.
Yeah, I think it can, yes, it's probably not, I mean, it's certainly not what you would think of as a direct implementation question. It does take a little bit of cleverness there. I think there is, maybe I'll share a link in Discord, like there's a nice set of shortest path based problems in one of these websites that curate CP practice problems. And perhaps this was inspired by, again, a problem in a contest like Nipun was saying. So I guess the more you see of these, the more I think, yeah, so this is, I guess, my cliched answer. So I'm sorry if you're tired of hearing this, but I guess the more of these problems you experience solving, the more you'll be able to, when you see a new problem, you'll be able to do some combination of ideas that you have seen from previous problems. So it's usually unlikely that if you have come out of just learning the shortest path algorithms and you encounter problems that involve non-trivial, as in, non-obvious variations, they may not strike you at once. And it's probably too much to expect that, it will strike you within the timing of a short contest, let's say. If it's one of the long challenges, that's a different thing. I think there you have enough time to really think through things. And if it's a long challenge, then I think you can probably come up with this by just brooding over it, trying different examples and things like that. But sometimes you do think that, is this a flash of insight or how does this work? But usually what happens is you just systematically collect and make notes of things that look really clever and things that make you go, okay, how would I come up with that? But when you have seen enough of these things yourself, you'll find yourself instinctively coming up with things where your friends are going to ask you, okay, how did you come up with that? And you're going to say, okay, that's probably because you've seen a lot of these things. And and then you come up with new things that are not just, it's not just repeating a trick you've seen before, but you just start getting a feel for it. So it's a bit hard to explain perhaps, but really as you practice more and more, like any other skill, then you start being able to create new ideas of your own, just over time. So I hope that helps at least a little bit. Yeah, it's
Yeah,
just.
and the first step is to know basically why your intuition won't work. So I just discussed two basic intuitions as to why they won't work, and then you can basically think of maybe trying all paths, and then probably it will give fail your time limits. And then there is this just create a new graph.
Right. Yeah, I think usually sometimes problems do have nice subtasks. I think unfortunately we don't do enough of that on the NPTEL questions, but usually in contests, especially CodeChef, I think have subtasks that will lead you to some maybe simpler approaches that will not work for the full set of test cases, but will at least get you started probably on some dead ends, but then you realize perhaps that okay, this is why this is the bottleneck here, or this is why this won't work with more general constraints, and you kind of build it up slowly. So yeah, I mean, I think that's so it's nice to practice problems that have subtasks. I guess that helps you at least get some initial footing and confidence, and also being able to I think it's good to, yeah, like Nipun just said, develop a sense of finding counter examples or figuring out why certain ideas won't work. So for me, at least, when I come up with something that I somehow have a gut feeling that it's correct, I kind of become attached to it. It's difficult for me to find fault with it and to really think against something that I've just come up with because I really want it to be correct. So I think you want to probably not have that kind of attachment, and really sometimes I literally think of it as code that somebody else has written that I want to, and you want to prove them wrong somehow. So whatever works for you, to put some distance between you and I mean, all of us have been there where something that we are sure is correct is giving us a wrong answer or is timing out or whatever. So, so I think having an eye for coming up with counter examples is also a very valuable skill. And in some contests, it's also helpful when you have hack rounds or like rounds where you are also invited to break other people's code. This skill is useful. That sort of a context as well. So yeah, cool. All right. So I think we are past the hour. I don't see any questions in the chat, at least. And Nipun, can you just quickly check if there's anything on YouTube? For some reason, my browser is kind of a bit stuck. So maybe you can just
Sure,
take
ma'am. I'll just check one.
Yeah. Okay. Yeah. Hey, Devansh. Yes.
Ma'am, the thing is, I couldn't actually join the classes before this because
Oh,
of some
okay.
family issues. But
Okay.
I'm really interested in this course. Is there a way I can give the exam right now and do the assignments? The previous one?
Sure. So so usually NPTEL considers like your top 10 assignments, and you probably have enough remaining that you should be. So, but you are registered for the course, right? Because I
Yes, ma'am.
guess.
I registered long back, but due to some
Okay.
family issues, I couldn't really give time to it.
Okay. Yeah. No worries. So I think I think the exam registration deadline is still I think that's still on. I'll quickly check and let you know. But yeah, and you can do, if you do the remaining assignments, I think you should still be in good shape in terms of getting a certificate. I think that should be very doable. But yeah,
Hello,
I
I think I
guess,
lost connection. Am I still audible?
yeah, you're audible. Yes.
Yeah, I just checked YouTube. I think there is. Yeah, I don't see any question.
Okay, cool. Take it. So I guess yeah, I'm just trying to look up the exam thing. I mean, The NPTEL homepage seems to still have a link to registering for the exams. So my guess is you can still do that. The exams are sometime towards the end of April. So let me just see if I can confirm that for you in a second. So I think there's, okay. I see. No, unfortunately, it looks like that for the Jan to June dates, the exam registration deadline was in fact towards the end of Feb. I think even the one where you can give late fees or so, that was the extended date was till Feb 21st. I can try to find out if an exception is possible, but generally because NPTEL is a fairly large scale operation, I think they find it difficult to account for exceptions. Having said that, this is a course that will run every semester, as far as I understand. So, or at least almost certainly once a year. But I think it will almost certainly run again in August. So maybe you can sort of audit the course if you
Yes,
like
ma'am.
until then.
Yes, ma'am.
Hannah. Just go through the materials, and it's going to be a fresh set of problems and a different exam in October, November, whenever. So perhaps you can do it then. Would that be all right? Yeah.
Yes, ma'am. That's cool. Yeah.
All right. Yeah. I'm sorry if you had, I mean, I'm sure, circumstances beyond your control, but yeah, I mean, I hope you can, continue to be around and engage in the rest of the course, and it'll hopefully be a less time consuming ride when you do it the next time, right?
Yes, ma'am. Thank you.
Okay.
Thank you so
All
much.
right. Yeah. Thanks so much for joining us as well, and the nice discussion that you all had. Thank you, Nipun and Yash. And yeah, I think I said we might be doing a bonus problem, but it's past the hour, so maybe we'll pick that up next week. So I think Gaurav was here, but I think we agreed that we will pick that up next week. So yeah, thanks very much everybody for joining, and especially for the nice discussion today. Appreciate the engagement. Good night for now. Have a great week, great weekend, and a great week ahead. We'll see you back next week, same time.